DKW Physics. I'm Mr. McConnelly. Today we're going to talk about electric fields. But I want to first start you thinking about this idea. If I have two horseshoe magnets here, you know all the way from your elementary school days that there's an attraction or a repulsion between these. Therefore, you're thinking, well, there's some sort of invisible field. There's some invisible field. We call that the magnetic field. And you guys seem to be comfortable. Most people are comfortable with that concept because they know, like, there's a magnetic field all the way around the Earth, and so when you hold a compass, it always points towards the north, and you're fine with that. But most people don't give a second thought or think at all about electric fields. Because if I do a similar demonstration relating back to yesterday, and I charge this one, and I charge this one up, because these are insulators, and I bring them close, there's going to be an attraction or a repulsion. Well, there must be an electric field between them. But you're not as familiar with electric fields because they don't affect you as often, I guess, or you don't notice them as often. But they're there, and if you think of a day where you wake up and your hair is staticky, there is an electric field around your head. If you think of walking up to a parked automobile and you reach out to open the car's hand or pull the door open and it shocks you before your hand gets there, there must have been a pretty strong electric field because you actually had electrons jump to your fingertips from the car. Okay? So I want you to think that in your mind, okay, there are electric fields. Good. Now, the next thing I want you to think about is, well, if I have an object here and I know it's charged, but I don't know if it's charged positive or I don't know if it's charged negative, how might you be able to tell? Well, what we say in physics is we put a test charge nearby. And by definition, a test charge is always a positive, okay? So you put a test charge and you note which way the test charge moves. So let's say the test charge goes and goes away. Then what's the charged object? What charge does it have?
Positive.
It's also positive. So see, you see how a test charge works. It's an indicator. It kind of tells you, and you can do the same with magnets. You're more familiar with that, but it's the same concept here. Well, so there's a convention that people came up with to draw electric field lines. Let's do a new picture. If you have a negative here and a positive here, then the electric field lines, the arrows, are going to point from the positive towards the negative. That's because, remember, these arrows are representing, if I were to place a test charge right here, which way would it move? No, it would move that way. So if you're trying to determine in your mind or think in your mind, oh, which way do those arrows go? Think about putting a little positive and think which way the positive would move, and that's the way you draw your arrow. So you're going to have electric field lines that are drawn somewhat like this. Now there's also going to be some, maybe a sketch and another one down here. But what I want you to note is as the electric field lines get spaced out further and further, what do you think happens to the strength of the electric field? It's weaker and weaker. So they call it the flux density. Flux density. It's how densely packed or how close together the lines are. If the lines are close together, that's going to tell you it's a strong electric field. If they're further apart, it's weaker. Kind of a basic idea there. Further, beyond that, there's actually an equation that can help you figure out the strength of an electric field. And it's simply the electric field is force divided by charge. This is in your reference table. This electric field. This is force in newtons. And this is charge in coulombs. So electric field is in a certain number of newtons per coulomb. As example, I looked up a couple reference numbers to that. In order to get a spark in the air, so if you see a little spark jump to your finger when you go to touch a car, or you move your legs underneath the sheets in the wintertime and you see sparks underneath the sheets, then you are seeing an electric field value of at least 3e6 newtons per coulomb. 3e6 newtons per coulomb. That's when you can see a spark in the air. If, for instance, we take and we charge up this rubber wand here, and we bring it close to our finger, you probably won't see a spark jump, so it's weaker, and in fact, that comes out to a value of about 1e3 newtons per coulomb, just to give you kind of a reference of how strong these are, how big these numbers are. Okay. Have you ever seen when someone's hair gets staticky? Which direction, or how do the hairs point on their head? Out, out, out. So if we draw a picture of a person here, here's my art skills for drawing a person. This is a person who has staticky hair. Their hair is sticking out like that. The way it relates to this lesson is that your hairs on your head, or any small object that's able to easily move with static electricity, the hair will follow or align itself with the electric field. So actually what you're seeing is when your hair gets staticky and it sticks out like that, you're seeing a visual representation of the electric field lines. Now how do you know if you're charged positive or charged negative? You have to introduce a test charge. Okay? My guess is usually you're charged negative. But, you know, it could happen the other way, I guess. So, you got the electric field lines seen in here. So let me, before we wrap this up, let's draw a few more pictures here. What would it look like, let me get some space, what would it look like if we got a picture of a positive and a negative charged object. What if we had two positive objects? What would the electric field lines look between those? Well, if you think of, placing a positive test charge anywhere near here, the arrows are going to have to come out. The arrows are coming out. The arrows are coming out. And that seems to lead to an issue here. Because now you got arrows like going towards one another. So what is going to happen when those arrows get close to each other is that they don't really like each other because, remember, like things repel. So you end up getting something like this. This could be a possible scenario. Those arrows are not, the electric field lines are not going to cross each other. They're going to deflect away from one another if these two things have similar charge. The other thing is, there's a special scenario, and it takes place in a capacitor. And I know you're not familiar with what capacitors are yet, but what a capacitor is it's two parallel plates. These are plates, parallel plates, and they're conductors. So they're like metal plates. And you connect a source of electricity, like a battery. So short, long, it's a symbol for a battery. You connect a battery to these parallel plates, and the battery's electrons, energy, start collecting on the plates. So what you end up getting is you get one plate that has a deficiency of electrons and one plate that has an excess of electrons. So do you think there's an electric field between these? Oh, indeed. Because you're piling up a lot of opposites. So the electric field has to move from the positive to the negative. Just making sure people are with me here. So your electric field is going to look like this. And it's probably a pretty densely packed electric field because these plates, I've drawn them really far apart, but in actuality they're pretty close together. So it's a pretty strong field. And this idea here is called a capacitor. And we'll spend more time on that another day. But what you need to know for now is that anywhere in the middle here, if I go to point A or point B, or point C. I'm just trying to represent random anywhere spots. The electric field strength is the same anywhere between a parallel plate capacitor. So the E field, electric field, is a constant, or it's the same number anywhere in between the two parallel plates. One more thing I want to add. What do you think the electric field is, the electric field strength is, in a conductor? So E field in a conductor. The conductor is usually a metal. What's the electric field in a conductor, since the electrons are free to move within the conductor? Well, the answer is you're going to have 0. You have to have an electric field in a conductor because you're not piling up excess electrons, or you don't have a deficiency of electrons. If you have a conductor, the electrons are going to evenly disperse themselves. It's going to spread out. It's going to move. The electrons are going to move away from being next to one another. So for today, that's electric fields, physics.